Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list published on March 6, 2026, just 3 days ago. It introduces a compact vision language model that bypasses traditional contrastive pre-training, instead initializing its vision encoder directly from a text-only large language model, hitting an impressive score of 96 on document understanding tasks. The paper is titled Penguin vs. L, Exploring the Efficiency Limits of Vision Language Models with Large Language Model-Based Vision Encoders. And as we'll see later, these results have significant implications for running advanced AI on compute-constrained mobile devices. And for those interested in the implementation, the authors have shared their code on GitHub. Alright, Figure 1 presents a benchmark comparison across various tasks, showing how the compact 2 billion parameter model stacks up against other options. The chart on the left covers image benchmarks, which are grouped by capabilities like optical character recognition, math, and knowledge. Next, the chart on the right displays video benchmarks, dividing them into long-form and temporal understanding versus general understanding tasks. In both of these radial charts, longer bars indicate better results. So, the prominent purple bars for Penguin vs. L clearly demonstrate its strong performance advantage across all these modalities. Okay. Figure 2 contrasts 3 approaches for training vision encoders. The left panel shows contrastive training, which aligns separate image and text encoders by pulling matching pairs closer together. The middle panel illustrates direct large language model supervision, where a vision encoder connects to a frozen language model, though this risks overfitting. Finally, the right panel details Penguin encoder training. By initializing the vision encoder directly with text model weights, this method uses a feature reconstruction loss to retain rich linguistic knowledge, making the alignment process much smoother. Well, after Figure 2 outlined the training approaches, Figure 3 maps out the complete unified architecture for Penguin vs. L, showing exactly how it processes both text and visual inputs. The standout feature is the vision encoder, which is initialized directly from pre-trained large language model weights. To make this text-based model understand images, its causal attention is converted to bidirectional attention, and it is equipped with two-dimensional rope positional embeddings, a technique that helps the model grasp spatial relationships in images. For video inputs, the architecture uses a temporal redundancy-aware token compression strategy. This mechanism dynamically assigns more tokens to keyframes, while compressing intermediate stable frames, allowing the model to efficiently process long video sequences before passing everything into the main language model to generate a response. So, after Figure 3 outlined the unified architecture, Table 1 details the performance of the 2 billion parameter model variants. The left side groups the evaluation benchmarks into distinct categories, spanning document comprehension, general knowledge, math, and video tasks. Then, focusing on the highlighted column, we see that Penguin vs. L secures the top spot in the majority of these tests, which are marked in bold. This broad success, especially against strong baselines like Qwen 3VL, validates that the text-driven vision encoder genuinely captures the fine-grained visual details needed for diverse reasoning tasks. Okay, following the strong benchmarks in Table 1, Table 3 breaks down the design choices using an ablation study. The top half isolates the pre-training phase, showing that starting with pre-trained language model weights provides a major performance boost over random initialization. This section also confirms that the relation loss, which helps the model grasp spatial connections between image patches, is critical for preserving fine-grained visual details. Finally, the bottom half compares the Penguin encoder against traditional models. The results demonstrate that the Penguin encoder achieves the highest average score, proving it can outperform established models like SIGLIP2, despite using significantly less total training data. Alright, wrapping up, the main takeaway is that better visual representation drives performance more than simply scaling up model size. By initializing vision encoders with text model weights, Penguin vs. L enables highly efficient, top-tier performance on compute-constrained mobile devices. That is it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.